Before we start with inverse of a matrix, here's some reminder of notation that is useful and some important results also. So first thing was to transform a linear system into a matrix form. So we have coefficient matrix here A, and then X will be the vector of unknowns, and on the right hand side we have a vector that we call right hand side member. So in matrix notation we write A for coefficient matrix, X for vector of unknowns, and B for the vector on the right hand side. So this system is called non-homogeneous system. Now if all of the entries of B are zeros, then we have something written like this, and it's called homogeneous system. And here we have augmented matrix form. Now the interesting part about homogeneous systems is that they always have at least one solution, because x1 equals 0, x2 equals 0, x3 equals 0, xn equals 0. That's always a solution for a homogeneous system. Sometimes that's the only one, sometimes we have infinitely many solutions for homogeneous system. So in case where we have more unknowns than equations, homogeneous system will have infinitely many solutions. Some reminders of identity matrix. So you have 1 by 1, identity 2 by 2, identity 3 by 3, 4 by 4. So we see that the identity is a diagonal matrix that has zeros off the diagonal, and the diagonal entries are all equal to 1. Some properties related to addition of matrices. So the first condition is that matrices are of the same size. So we can only add matrices that are of the same size. So let's say two matrices 2 by 7, we can add them. Two matrices that are 3 by 5, we can add them. But if one matrix is 2 by 6 and the other one is 2 by 4, we cannot add them because the size is not the same. So the size must be exactly the same in order to add two matrices. The resulting matrix will have the same size. We can add in any order we like. If we add 0 to a matrix, well, we have the matrix unchanged. Also, we can have negative of a matrix. So when we add a matrix with some negative of itself, we get 0 matrix. And also we can change order in addition. A plus B is equal to B plus A. Now, a very important thing to realize is when we do the product of matrices, we cannot swap the order of matrices, we cannot interchange the order. So A times B is not equal to B times A. So the order is extremely important. We need to pay attention to that. Here are two matrices 3 by 3. We did the product AB, we got 3 by 3 matrix here, and BA is another 3 by 3 matrix, and we see very well that they are different because they have different entries inside. So clearly AB is different from BA, so that's super important to remember. Another interesting thing is when we have square matrices, A square is actually A times A, so we need to do the proper matrix product. We cannot just square numbers inside A. That doesn't work that way. We need to do the proper product of A times A. A cube is A times A times A, so we need to do again proper product. We cannot just cube everything inside A. That doesn't work that way. We need to do the proper product. Another interesting thing is when we have square of a summation of two matrices, obviously they need to have the same size and they need to be square. So A plus B squared is actually A plus B times A plus B. Now we distribute properly, so we have A times A plus A times B plus B times A plus B times B. So we know that A times A is written as A squared, and B times B is written B squared. Something similar happens with the square of the difference of two matrices. So this is different from what you have in polynomials or real numbers. Matrices are special species, and we need to be careful when we do the product of matrices. Order of multiplication is extremely important. So here, if we have product of three matrices with appropriate sizes, so that the product is actually defined, we can multiply any two that are next to each other. So here we multiply B and C first, and then the result, A is multiplying the result. That's the same as if we multiply A and B, and then the result of that multiplication is multiplying C. Here we have distribution, so A plus B times matrix C. So if we distribute, is AC plus BC. Here something similar, C times A plus B is going to be C times A plus C times B. If we multiply matrix by identity matrix, we can keep our matrix unchanged. So obviously, if my matrix is not square, the identity must be different in the size depending if I am multiplying from the right or from the left. That's nothing special. And if we multiply a matrix by a zero matrix, we end up with a zero matrix. Obviously, we need to make sure that the inside dimensions fit. With the transpose of a matrix, transpose is basically a matrix that we obtain by taking rows of A and then putting them in columns of the transpose. So first row of A becomes first column of A transpose, second row of A becomes second column of A transpose, and we continue like that. So obviously transpose of A is A itself. So we just close the circle. And transpose of a summation, well, it's summation of transpose matrices. So that's what we would like to see, and that's true. Now, if we have a matrix that is equal to its transpose, that matrix has a special name. It's called symmetric matrix. Something that we need to focus on is the transpose of the product, because this is very different from what you expect. Transpose of the product of two matrices is product of transpose in reverse order. So transpose of A times B is B transpose times A transpose. Something similar happens if we have a product of three matrices, obviously with sizes that fit. So transpose of a product of three matrices is C transpose times B transpose times A transpose. If you have four matrices, it will be similar. So we reverse the order of multiplication of the transpose matrices. If I have a number times a matrix and I transpose that, well, it's the same as multiplying the transpose of a matrix by that number, so nothing special. This is the normal law of addition of exponents, so that's what you would expect anyways. So the only super important thing to remember is that transpose of the product, we need to reverse the order of multiplication of transpose matrices. Something similar will be seen also when we deal with inverse of a matrix. So now the inverse of a matrix. So that's something that we need to see very carefully. First thing to notice is that only some extremely rare matrices have the inverse. So if you pick a random matrix, chances are that matrix does not have an inverse. So some extremely rare matrices have the inverse. What we can notice is that the inverse, so when inverse actually exists for a matrix, that inverse is unique. So first thing is, if my matrix is not a square matrix, so let's say 2 by 7, then I know that since it is not square, it does not have an inverse immediately. So those matrices that do not have inverse, we have a special name for them. They're called singular matrices or non-invertible. So if my matrix is not square, I know immediately it is not invertible. It does not have an inverse. Now, what happens when I have a square matrix? Well, some square matrices, they do have inverse, some they don't. So if I have a square matrix, actually I don't know what's going to happen. Maybe my matrix has an inverse, maybe it doesn't. So if my square matrix has an inverse, we call that matrix invertible or non-singular. Most of the time we use invertible. So how can I know actually if my matrix has an inverse or not? Well, the definition of the inverse, so I have my square matrix A, and my square matrix A is invertible if and only if I can find a matrix B that is also n by n, such that A times B is equal to identity n by n, and also B times A is also equal to identity. So that's a definition of the inverse. So my matrix A has an inverse B if and only if A times B is equal to identity. Now inverse is unique, which means that if B is inverse of A is inverse of B. So that's what we have here. If B is inverse of A is inverse of B. So here we have two matrices, and if we do the product, we will get identity 2 by 2. And if we do A times B, we get identity 2 by 2. If we do B times A, we get identity 2 by 2. So what we say is that matrix A is invertible, its inverse is B, and it's unique inverse. There's no other matrix 2 by 2 that is inverse of A. But also at the same time, we know that B is invertible and the inverse of B is the matrix A. So they come together and they are unique to each other. So A is inverse only for this matrix B and no other matrix in the universe. And B is inverse for this A and no other matrix in the universe. So they are very linked and very special. So our inverse is always unique when it exists, obviously. If the inverse exists, this is notation. We write A, and then in the exponent we write -1. So it is important to notice that this is just a notation. What this means is inverse A, or A inverse, depending how you like it. We remember that we have not defined division by a matrix. So there is no such thing as dividing a matrix. So 1 over a matrix, that's not defined. A matrix divided by another matrix is not defined. We only have defined addition of matrices and product of matrices. Division of matrices is not defined. So this is not 1 over A, okay? And it's nothing to do with just reversing the entries of A. Nothing, nothing, nothing. So this is just a notation saying that this is inverse of A. Okay? We will see later how to compute properly inverse. And obviously, if the inverse exists, we can multiply it by itself. So inverse squared or inverse to power 3, to power 4, to power 5. So this is just a notation. Again, this is notation for the inverse of A. Instead of writing ENVA, we write this way. It's faster. Now, if I have two matrices of the same size that are invertible, their product is also invertible. So product of two invertible matrices is also invertible. Not only that, but we know what is actually the inverse. So the inverse of the product of two invertible matrices, AB, is B inverse times A inverse. Again, you see how we swapped the order of matrices. Something similar happened when we did the transpose of the product. Similarly, if we have three invertible matrices of the same size, A, B, C, and we want to compute the inverse, inverse is actually C inverse times B inverse times A inverse. Similarly for product of four matrices, and this continues obviously. You notice that we reverse the order. Now, if I have an invertible matrix and I multiply by a number, and my question is now, what is a number times a matrix, and then what's the inverse of that? Well, it's 1 over the number times the inverse of the matrix. Obviously, the number needs to be different from 0, because 1 over 0 is not defined. By the way, matrix 0 n by n is not invertible. because any other matrix n by n you use, when you multiply them, you get 0 n by n. You never get identity. So a 0 matrix n by n is not invertible. It does not have an inverse. So be careful. Obviously, if we have 10 invertible matrices with the product, something similar happens. With the order, it's all swapped. It is obvious that inverse of the inverse is your original matrix. So inverse of the inverse of A is A. So that's normal. Transpose of the transpose of A is A. So something similar. Now what is interesting is when you have your square matrix that is invertible, so has an inverse. Good news is that the transpose of that matrix also has an inverse, so it is invertible, and we don't need to struggle to find it. Inverse of the transpose of A is actually transpose of the inverse of A. So this is a fantastic result. We need to remember that because it's very helpful. Now, something happens with the linear systems when we have our coefficient matrix that is n by n and invertible. In that case, any linear system having this matrix as coefficient matrix has a unique solution. So Ax equal b for any b you can choose has a unique solution, and the solution is given actually by the product of inverse of A times b. So this is something to remember. So if we have a system that has a square coefficient matrix and that matrix is invertible, then the system Ax equal b has unique solution for every b. So for every different b we will get one unique different solution because our matrix is invertible. So this is a very important property to remember. Also, if b contains only zeros, then we have a homogeneous system. In that case, because matrix A is invertible, our homogeneous system will have one unique solution, which will be inverse of A times 0, which is 0 vector. So when our square matrix A is invertible, homogeneous system Ax equals 0 has unique solution x equals 0. Now, in some cases, we are able to compute easily the inverse. For instance, if our matrix is identity matrix n by n, well, the inverse is identity matrix n by n, so it's matrix itself. So inverse of identity 2 by 2 is identity 2 by 2. Another example of easy computation for the inverse is when we have diagonal matrix and all of the diagonal terms in the matrix are different from 0. In that case, it's very easy to find the inverse. It will be again a diagonal matrix, and the entries are 1 over the entries of the original matrix. So 1 over A, 1 over B, 1 over C, 1 over C, D, 1 over E. Obviously, every single one of those entries must be different from 0. If it is not, then you don't have an inverse. So those are easy cases where you have identity or diagonal matrix. It's easy to find an inverse if all the entries on the diagonal are different from 0. If one of them is 0, then bye-bye, that matrix doesn't have an inverse. In the case of 1 by 1 matrix, which is very rare, we don't use those. When the entry is different from 0, inverse is 1 over the entry. Obviously, if the entry is 0, our matrix is 0, and 0 matrix does not have an inverse. So this one would not be invertible. For any other value of C different from 0, inverse of 1 by 1 matrix is here. In the case of 2 by 2 matrix, here we have 2 by 2 with entries A, B, C, D. There's a condition, and this number here is called determinant. We will see that later. So if the determinant is different from 0, my matrix is invertible, and we know what's the inverse. Inverse is given here. 1 over the determinant times 2 by 2 matrix, where we just swapped A and D and put negative signs in front of B and C. So you can remember this formula if you wish for 2 by 2, and it is valid only for 2 by 2. Or later on you can use our classic method that I will show in a moment. So the condition is very important. If AD minus BC is different from 0, let's say it's 7, then we know that our matrix 2 by 2 has an inverse, and an inverse is given by this formula all the time. Now, if the determinant is 0, then the matrix is not invertible. So it is singular. And this will be something that we will have as a result later on. Whenever the determinant is different from 0, the matrix is invertible. If the determinant is equal to 0, matrix is not invertible. So again, you can remember this formula or use this general algorithm that I'm presenting now. So a very important result is this one here. If we have an invertible n by n matrix, so that matrix is invertible if and only if its reduced echelon form is identity. So let's say I have 5 by 5 matrix, and that matrix will be invertible if and only if the reduced echelon form of that matrix is identity 5 by 5. Which also means that my matrix is not invertible if and only if its reduced echelon form is not identity, which means that we have at least one row of zeros. So this will be something that we will use very often, and I will show you examples. So inversion algorithm is simply applying our elementary row operations and Gauss-Jordan to a special augmented system. So in this system I have my matrix A, which is a square matrix, so let's say 5 by 5, and slash, and then on the other side I have identity 5 by 5. And now my goal is to apply elementary row operations and Gauss-Jordan method to try to get identity matrix as a reduced echelon form on the left side. Okay, so that's the goal. If I'm successful, that means if my matrix has an inverse or if my matrix is invertible, then I will end up at the end of my Gauss-Jordan with identity on the left side, and on the right side, whatever you see will be the inverse of your original matrix. So that's if we are successful in our process. Now, A is not invertible if and only if at some point during the Gauss-Jordan process we have a row of zeros on the left side, which means we have a contradiction somewhere. And we remember when we were solving the linear systems, as soon as we hit a contradiction, which means a row of zeros on the left side slash some number different from 0 on the other side, then we say, oh, this is a contradiction, system doesn't have a solution. Something similar happens here. The system that I'm solving will not have a solution, therefore my matrix will not be invertible. So example here, I use simple example at this stage. So I have my 3 by 3 matrix here with a lot of zeros to help me, and I have my special augmented matrix. On the left side I have matrix A slash, and on the right side I have identity 3 by 3 because my matrix is 3 by 3. If my matrix is 7 by 7, on the right side I will have identity 7 by 7. Okay, so my goal now is to apply elementary row operations and Gauss-Jordan process. That's all. So my goal is to put 0 below my leading entry. So I have 2 here in the row 3, I need to take care of that. So I replace row 3 by row 3 minus 2 times row 1. So row 3, entire row, everything is replaced by row 3 minus 2 times row 1. Okay, let's go. So 2 minus 2, 0, 0 minus 0, 0, 1 minus 0, 1. And then here I have 0 minus 2 times row 1. So 0 minus 2, the result is minus 2. Be careful. 0 minus 2 times 0 is 0, fine. And then 1 minus 2 times 0 is still 1. So again, be careful here. We had 0 minus 2 times row 1. So 0 minus 2 times 1, which was minus 2. Be careful. We are applying the elementary row operation to the entire row, everything. Now it's good. I have this entry here that I would like to be 1, and if I divide, so I multiply basically row 2 by 1 over 2. So I multiply row 2, entire row, by 1 over 2. So I'll get 1 here, but I'll get 1 over 2 on the other side. So be careful, we are applying elementary row operation to the entire row, everything. So now, good news, on this side, on the left side, I have reached my reduced echelon form, which is identity matrix 3 by 3. And that's exactly what I wanted. On the right side, this matrix, I know it is inverse of my original matrix A. So this is the inverse of original matrix A. I could verify that by doing the product A times this matrix. If the result is identity 3 by 3, then it's true. This is the inverse here, inverse of A. You can do the product yourself and make sure that you get identity 3 by 3. So this matrix here is the inverse of original matrix A. Also, we know that original matrix A is the inverse of this matrix. So they are inverse of each other. And again, the process is apply Gauss-Jordan and elementary row operations on a special augmented matrix form. On the left side, you have your matrix slash, on the right side, you have identity with the same size. And then you go and apply elementary row operations to the entire row. Here is an example, again, simple one, to illustrate when we do not have an inverse. What happens? So I have my matrix 3 by 3 again, augmented matrix form. On the right side, I put the identity 3 by 3. Now, again, I want to produce zeros below my reading entry. So I have 1 and I want to produce 0 in the entry 3, 1. So the entry 2 here. So I replace row 3. So the entire row 3 by row 3 minus 2 times row 1. So I replace entire row 3 by row 3 minus 2 times row 1. Everything. So we do the computation, we get 0, 0, 0 on this side, and again we have 0 minus 2, 0 minus 0, fine, and 1 minus 0, 1. So I get this. And notice here on the left side I have a row of zeros. That's a problem. We know that this will create a contradiction because left side pretty much says that 0 is equal to negative 2, which is false. And it says also 0 is equal to 0, fine, but also it says 0 is equal to 1. No good. As soon as I have one contradiction, it's game over. So technically, as soon as on your left side, in your Gauss-Jordan process, as soon as you reach a row of zeros somewhere in the matrix, you need to stop. You stop the process, there's nothing else to do. You know that your original matrix A does not have an inverse. That's a singular matrix, there's nothing you can do about it. So this row of zeros is something that will indicate that our matrix is not invertible. When things, let's say, work, we end up with identity as reduced echelon form on the left side. On the right side is the inverse. That's when it works well. Now, if it doesn't work, what will happen is that systematically on the left side at some point you will have a row of zeros. As soon as you see that, you need to stop. There's nothing else to do. You just say, okay, there's a contradiction in the system, goodbye, matrix A is not invertible. It does not have an inverse, and there's nothing we can do about it. A quick revision for inverse, the theory: if I have a square matrix A, then another square matrix B is the inverse of A if and only if A times B is equal to identity n by m. And also B times A is equal to identity n by m. If one of these is true, because they are both square, if one of these is true, then B is inverse of A. I don't need to verify this one. So if this is true, then A is inverse of B and B is inverse of A. Inverse is unique. If a matrix has an inverse, it has only one in their universe. So A is inverse of B if and only if B is the inverse of A. So they are inverse of each other. And we use the because it's unique. When a matrix has an inverse, it is unique. And this is how you can verify. If I tell you, here's a matrix A, here's matrix B, is B inverse of A? All you need to do is do the product, A times B. If you get identity of the same size, well, you're done. That proves that A is an inverse of B and B is inverse of A. You don't even need to do this part. As soon as you do one of them and you get identity, it's good. Now, what is worth noting is, if my matrix is not square, if I have, so a m by n, and m is different from n, so let's say 2 by 7, then a 2 by 7 matrix is not invertible. If my matrix is not square, it is not invertible. That's easy. Now the problem is, when my matrix is square, sometimes the matrix is invertible and sometimes it is not. And for now, we don't know how to differentiate when it is, when it is not. We need to go and compute. We have a method to compute, and then we will know by computing. Later on, we will learn more tools, and then those tools will help us figure out if our matrix is invertible or not. Even though to compute, we have our unique tool to do it. Okay, so if our matrix has an inverse, inverse is unique. So easy case, 2 by 2. So I have square matrix 2 by 2. With entries A, B, C, D, and this matrix is invertible if and only if this condition is satisfied. Later on we will see that this is called, this number here, AD minus BC, is called determinant, and as a general rule, when determinant of a matrix is different from 0, matrix is invertible. When a determinant is equal to 0, matrix is not invertible. So that's pretty much the condition that we have here. So it says matrix 2 by 2 is invertible if the determinant is different from 0. And on top of that, we also know how looks the inverse. So the notation for the inverse is A, and then in the exponent we write minus 1. So this is not A to power minus 1, it's just notation. Instead of writing E and V, I could write E and V of A, but that's too much. It's faster to write like this, A and the exponent negative 1. So in the case of 2 by 2 invertible matrix, here's how we compute the inverse. 1 over the determinant, and then in the matrix you see B and C, they got minus in front, and A and D, we swap them. See AD, here is DA, and the diagonal. So if I have a cute matrix like this, can I compute the inverse? First thing is to verify the condition. So I have 1 times 4 minus 2 times 3. So 4 minus 6 is negative 2. So this is different from 0. So A has an inverse. So I know it. The inverse exists. Now I will be able to compute it, and A inverse is given by 1 over the determinant. The determinant was negative 2, so 4 minus 6 was negative 2. So it's 1 over the determinant times, we swap 1 and 4, and then in front of 2 and 3 we put in minus sign. So that's it. If you wish, you can put the fraction inside or leave it as it is. It's up to you. It doesn't change anything in life. So this will be negative 2 and 1, 3 over 2, and negative 1 over 2. So you can write it, keep it like this or like this. It's up to you. So this is the inverse of this matrix. How can I verify? Easy. I just do the product. A times this expression of this matrix, so this matrix times this matrix. If the result is identity 2 by 2, yes sir, we have the inverse. Okay? So normally you're supposed to do that in life to make sure. You're not going to waste any time on that, but you can do that if you wish to make sure that what you computed is actually the inverse. The only condition for the inverse is then when you do the product, you get identity of the same size. So here, A times this matrix, if you get identity 2 by 2, that means that this is inverse of A, and also A is inverse of this matrix. So they are inverse of each other. Some other examples. So this matrix here, so I have 1 times 4 minus 2 times 2, so this is 4 minus 4, 0. Oops. This means that this matrix doesn't have an inverse. Why? But the determinant is 0. That's why. So you see, you have a cute matrix. There's nothing wrong with it. It just doesn't have an inverse. So a matrix does not need to have an inverse, but if it has an inverse, it's cute. Then we have some properties. So another one. So let's compute. Have 3 times 2 minus 5 times 1. So 6 minus 5. So this is 1 different from 0. So A has an inverse. How do I know? Well, the determinant is different from 0. And the inverse is given by this expression is 1 over the determinant, determinant is 1, divided by, I swap the diagonal terms, and then I put the negative sign in front of the other two guys. So this is what I have, so this is 1. So these two matrices are inverse of each other. We can verify 6 minus 5 is 1. So if I do this times this, I get 1. And then this times this is negative 15 plus 15, that's 0. 2 minus 2, that's 0. Minus 5 plus 6, that's 1. So if I do the product, I'll get identity 2 by 2. So that means that these two matrices are inverse of each other. Important thing to notice is an easy case. All identity matrices, 1 by 1, 2 by 2, 3 by 3, 7 by 7, 1 million by 1 million, they are all invertible. And the inverse of identity matrix is identity matrix itself. That's great, beautiful. And all the square 0 matrices, so the matrix full of zeros inside, well, they are not invertible, obviously. If you just check the definition, you cannot find any other matrix such that 0 matrix times that matrix gives identity. When you multiply 0 matrix times any other matrix, you're gonna get 0 matrix, no other choice. So that explains that 0 matrices do not have inverse. Another easy case are diagonal matrices. So we remember diagonal matrix is the one that has 0 off diagonal. On the diagonal you can have whatever you want. So if the diagonal entries are all different from 0, then diagonal matrix is invertible. So since all the diagonal entries are different from 0, D is invertible, this diagonal matrix. The good news is that we know how it looks the inverse also. The inverse is simply a diagonal matrix that has on diagonal 1 over the diagonal terms of D. So it's going to be 1 over 2, okay, the rest is 0 here, then 1 over 7, and then negative 1 over 2. This goes for any diagonal n by n. What happens if I have 0 on one of the diagonal entries? Well, that's no good. So let's say I have a matrix E that is 2, 0, 0, 0. Well, this is diagonal, fine, but I cannot compute 1 over 0. So this matrix does not have an inverse. of the diagonal entries is 0, that's no good. So whenever you have a diagonal matrix, you check your diagonal entries. If none of them is 0, good, you can compute the inverse easily by 1 over the value. If at least one of the diagonal entries is 0, game over, that matrix does not have an inverse. So those are the easy cases. So let's now compute an inverse for, let's say, 3 by 3, and the process will be similar for 10 by 10. It's just 10 by 10 is going to take longer, a couple of days. So we have something called inversion algorithm. It's just a sophisticated name to actually apply Gauss-Jordan process and elementary row operations. So here's the trick. What we want when we have 3 by 3 matrices, 4 by 4, 5 by 5, 10 by 10, well, these tricks that we had, they don't work. Now we need a clear method. What we want is to start with our matrix A, an identity of the same size, and then apply Gauss-Jordan, hoping that we will end up with identity on this side as a reduced echelon form, and on the right side we will have the inverse. Whatever is here will be inverse. Well, that's if everything goes well. So if my matrix A, we can transform it through elementary row operations and Gauss-Jordan into reduced echelon form identity. Well, good news, that matrix A is invertible, and on the other side is actually the inverse. Now it could happen, and it will happen from time to time, that when the matrix is not invertible, during the process of Gauss-Jordan, at some point we had a row of zeros on the left side, and then both we need to stop, because that means there's a contradiction in the system, that means there's no solution, that means my matrix A is not invertible, and we can do nothing about it. So when we start this process, either we hit a row of zeros at some point, somewhere. As soon as we have it, we need to stop. We say, okay, matrix A is not invertible. Or we are lucky, and we keep going, and our reduced echelon form will be identity. In that case, whatever is on the other side is the inverse of our original matrix A. So how do I know that? Well, I can multiply them and see. So let's apply this to a couple of examples, just to see how it works. And it's the same procedure if I have 3 by 3 matrices or 7 by 7. Obviously 7 by 7 is going to take half an hour to do. So I'll find the inverse, if it exists, of A, and I'm going to give A. So A is a 3 by 3 matrix. Make sure we don't make any errors. So this is my 3 by 3 matrix, A, and the question is, can I find the inverse for this? So what we do, we start the process by writing an augmented matrix form. Slash, and then on the other side we put identity 3 by 3. So that's what we do. That's our procedure. This is one, I'll just put it in the right place. So this is the beginning. Now our goal is to produce reduced echelon form on this side. Hopefully it's going to be identity. If it's not, then we don't have the inverse. So let's see what we do. Well, we can apply any of the elementary row operations, anytime. Our goal is at the end, hopefully, to converge to reduced echelon form. That's our goal. So how we get there, well, it's our business. Obviously, we can divide by 2 the first row and create fractions immediately. So that will complicate our life. We can do that, that's legal, that's no problem, that's fine, but I don't like fractions. I already have problems computing like this. So what I'm going to do is I'm going to swap row 1 and 2, which means row 1 and 2, they need to swap. So that's what I'm going to do, swap row 1 and 2. Because at least that way I will generate 1 in the corner. So be careful, you need to take the entire row, huh? Everything. So we swap rows on both sides. This is like special augmented matrix form. And then the last one stays the same. So you see what happened? Row 1 became row 2 here. And row 2 became row 1. Make sure you don't make any errors. So each time we do one step, we double check. That way we know that whatever happens next is okay. So now I can produce zeros in these two positions. So I replace row 2 by row 2 minus 2 times row 1. And also I'll do the same for row 3. So let's go. Copy the first row properly, slash. Obviously, in all the process, there is no guarantee that at some point you will not have fractions. Well, fractions are in life, what can we do? So 2 minus 2, 0, minus 1 plus 2 is 1, and then minus 1 plus 0 is minus 1. Oh, now be careful. Row 2 minus 2 times 1 minus 2 times 0 is 1. 0 minus 2 times 1, so 0 minus 2, so that's minus 2, be careful. 0 minus 0, 5. So double check, this is 0, negative 1 plus 2 plus 1, okay. Negative 1, 1, okay. 0 minus 2, 5. Last one, row 3 minus 2 times row 1. This minus minus 2, so that's 1 plus 2, that's 3. And then 0 upstairs, it's fine. So again, 0. Careful here, I have 0 minus 2 times, so it says minus 2 times row. So 0 minus 2 times 1, okay. And then 1 minus 0. Good. Again, make sure everything is okay, especially the other part. So 0 minus 2, fine, good. Okay, very successful. Now I have my leading entry here and I'm going to kill this guy. So I come and I say I replace row 3 by row 3 minus 3 times row 2. Ta-da! So copy row 1, hopefully no errors. And then row 2. Now working on row 3. So row 3 minus 3 times row 2. So this minus 3 times this is 0. 1 minus 3. So 1 plus 3. 4, 0, 0, fine. And then negative 2 minus 3, negative 5. Oh, it's ugly. This is ugly. And then I have 1. Oops, 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 oops. Error, error. You see? I'm supposed to work on this row. Okay, let's go back. You see? 0 minus 3, 0, fine. 3 and 1, 4, good. So I'll go back. 0 minus 3, negative 3. Aha. Minus 2 plus 6, 4. Polite. And then 1 minus 0. See, we make errors, but our verification helps us spot the error. So the error was on this side, it was fine. I was able to do it right. So 1 plus 3, 4, and then, but here I screwed up. So I had negative 3, and then plus 6, 4, okay, good. So now what I have here is upper triangular matrix. Later on we will know that upper triangular matrices are invertible if and only if the diagonal terms are different from 0. So this one is, so I know everything is going to be fine. Divide by 4 to get 1 here. So row 3 is replaced by 1 over 4 times row 3. Good. So let's go. Negative 3 over 4. Okay. We have fractions. What can we do? Now my goal is to kill this guy here. So what I do is replace row 2 by row 2 plus row 3. That will take care of this guy. So if I add them, I get 0 here, negative 3 over 4, 1 over 4. Okay, so now I need to add. So this is 4 over 4 minus 3 over 4, so that's 1 over 4. Negative 2, my god. Negative 2 plus 1, negative 1. And this is 1 over 4. Well, it's becoming ugly. But I still have only 1. I need to kill this guy here and I'm good. So row 1 replaced by row 1 plus row 2. Negative 3 over 4, 1 over 4. Second row stabilized, we don't change it. And now the row 1. So these two add. Okay, addition, I'm good. Especially when I have zeros. So on this side I have identity, 3 by 3. This is my reduced echelon form. And on this side I have the inverse of A. So A inverse is the 3 by 3 matrix that is super ugly. 1 over 4, 0, 1 over 4. And there's a lot of 1 over 4 here. If I was smart, I would take 1 over 4 out. Okay, so this matrix is the inverse of matrix A. And matrix A is inverse of this matrix. Let's see now what happens when the things don't work out well. So question, find the inverse of this matrix here, A. So first step, put my matrix slash identity 3 by 3, because this was matrix 3 by 3. If it was 7 by 7, I would have identity 7 by 7, and finish by tomorrow morning. So let's see what happens here. Well, I have 1 here and I like 1. I would love it to be up, so I will swap row 1 and row 2. So swap them. Be careful, you need to swap these two also, the entire row with the entire row, everything. So we swap it, we have it here. Beautiful. So I have my 1 in the corner, that's what I wanted. Let's put 0 here. So I need to replace row 2 by row 2 plus 3 times row 1. If I do that, negative 3 plus 3 is 0, negative 6 plus 6 is 0, 3 minus 3 is 0. 1 plus 0, 0, 1 plus 3 is 3, and 0 plus 0, 0. But I notice that I have a row of zeros on the left. Whoa! I see the contradiction. This equation says 0 is equal to 1. Well, it's not. Bye-bye. It also says 0 is equal to 3. No, it's not. 0 equals 0. Okay, fine. Whoever cares. But 0 is not equal to 1, and it's not equal to 3. There's a contradiction. As soon as I have one contradiction, it's over. Another way of seeing it, as soon as you have a row of zeros on the left, you stop. There's a contradiction, stop, there's nothing to do. You have row of zeros, that's a signal to stop. That means that my matrix A does not have an inverse. Poor matrix A. There's nothing wrong with it, it just doesn't have an inverse.
Other ways of saying the same thing, it doesn't have inverse. A is non-invertible. Another thing, A is singular, just vocabulary. So as soon as you hit the row of zeros on the left side, you stop. Contradiction, stop, and matrix does not have an inverse. Finished. So my matrix from the beginning doesn't have an inverse. Goodbye. Nothing we can do about it. Another example of the same thing. I have a matrix, 3 by 3 again. Put it on the left, slash identity 3 by 3. Well, good news is I have 0 here. Let's put 0 here. So row 3 replaced by row 3 minus row 1. Do the operation. I get this. And on the other side, I get this. So I need to apply the operations to entire row. Okay, fine. Now I need to kill this guy. I could divide by 2, but I'm lazy yet. I can kill this guy easily. So row 3 replaced by row 3 minus 2 times row 2. Row of zeros. On the other side, I have some numbers anyways. Row of zeros, I need to stop. There will be a contradiction. There's nothing I can do. My original matrix A does not have an inverse, so it's not invertible, and it's singular. Those are different ways of saying the same thing. A does not have an inverse. A is non-invertible. A is singular. It's not its fault. What can you do? Row of zeros. On this side, you will never have row of zeros. You started with your identity, and you cannot kill these numbers. They will stay there. You will never have a row of zeros on the left, on the right side. If you have it on the left, you need to stop. On the right side, you will never have them. So be careful whenever you see in your Gauss-Jordan process row of zeros, you need to stop. Your matrix doesn't have an inverse. Bye-bye. There's nothing you can do. Remember, one of the important things is that when I start with a square matrix, I apply Gauss-Jordan process. By the end, either I have identity matrix as a reduced echelon form, or my reduced echelon form has a row of zeros. Okay? If my reduced echelon form has a row of zeros, my matrix is not invertible. And on the other hand, reduced echelon form is identity, then matrix is invertible. And as soon as we get a row of zeros somewhere in the process, it's over. We know that our reduced echelon form, even if we push further, which makes no sense to do, but even if we push, we will have our row of zeros still there. Nothing can change. So that's why there's no point of continuing. As soon as you hit row of zeros, you stop. And you can have row of zeros in the middle of the matrix, doesn't matter. Wherever you have it, you stop. It can happen on row 2, row 3, row 75, doesn't matter. If you have row of zeros, you're lucky, you don't need to continue working. So you just call it a day and you say, here is a problem, we have row of zeros, our matrix is not invertible, there's nothing we can do about it.